Okay. So we're going to take a look now at the ideal gas law. Okay. You're going to use the ideal gas law as an equation of state. So this law will be used when you do not have conditions changing. Your pressure is not changing, temperature is not changing, volume is not changing, and the number of moles of gas is not changing. That's when you're going to use your ideal gas law. The other gas laws were used when one variable was changing, okay, or more than one variable. So let's look at our ideal gas law. Let me share my screen here. This shouldn't take too long. Okay. All right, let's get some lines on this paper. All right. All right, ideal gas law. It deals with all of these variables and ideal conditions. What are ideal conditions for gases? Well, they like to have low pressures and high temperatures. So when the pressures are low enough and the temperatures are high enough, this gas law works to identify unknown variables. The ideal gas law is PV equals nRT. Some people call it the Pivnert equation, right? Or the pervert equation. This is obviously your pressure. This is obviously your volume, and your volume must be in liters. Must be in liters. You cannot plug in a milliliters into this problem. It will be wrong. Your N is your number of moles of gas. And in order to use this gas law, you must be dealing with gases. Okay, you can't plug moles of solids or liquids in here. R, we will get to. It is more, we need to leave some space for this. This is our universal gas constant, and we need to discuss that a little. Oops, universal gas constant. And then here we've got our temperature, which once again must be in kelvins. All right, so let's talk about our universal gas constant, R. The value used is dependent on the unit of pressure. So there are several different R values. And the one you use depends upon the unit that your pressure is being measured in. If your pressure is measured in atmospheres, okay, then let's put that into a chart, right? That'll be easier, less words. Let's write units pressure, and then let's write R values, okay? What does that mean? It means if your pressure is measured in atmospheres, or if you want to solve for a pressure in atmospheres, your R value needs to be 0.08206, all right? And then look at the units, that is liters, atmospheres, per mole Kelvin. All of those units follow that number. If your unit of pressure is kilopascals, then your R value will be 8.31 liters kilopascals per mole Kelvin. If your unit of pressure is in millimeters mercury or torr, remember they are the same, your value for R will be 62.4. And that will be liters mmHg, millimeters mercury, moles Kelvin. And it's as simple as that. You just plug in. Notice you're solving for moles. So you can then relate moles to mass, or you could be given mass and need to relate your mass to moles in order to use the equation. One more thing I need to get in here is that at STP, right? What is STP? This means standard temp and pressure. right? Standard temp is 0 degrees Celsius or 273 kelvins. Standard pressure, we've already discussed, is 1.00 atm. At these conditions, 1 mole of any gas has a volume of 22.4 liters, and that is at STP. So if the conditions are standard, meaning the temperature is 0 degrees Celsius and the pressure is 1 atmosphere, then it is always true that 1 mole will equal 22.4 liters. You can plug it into the gas law. You can make this standard. You can make your number of moles 1. You can plug in your R, and you can plug in your standard temperature. And when you do that and you solve for volume, it will be 22.4 liters. Okay, if this is 1 atmosphere, right, and the volume, and you have 1 mole, right, and we have 0.08206, and our temp is 273 kelvins. When you solve for your volume here, right, when you solve for this, it will be, what will it be? It will be 22.4 liters. That is a horrible color. Let's fix that. At that case, your volume here, right, will be 22.4 liters because your pressure is standard and your temperature is standard. So we know this to always be true. All right. Now let's look at a word problem. What pressure? All right, let's start pulling out our variables. Okay, start writing things down. What pressure, question mark, is required to contain, and these are moles, so there we go, 2, 3 moles, nitrogen, that's N2 diatomic, 4.2 liters, that's a volume, equals 4.2 liters. And then we have a temperature of 20 degrees Celsius. Go ahead and add 273. That makes 293 kelvins. Notice that I do not have 2 of anything. I've got pressures, volumes, and my thing just died. We've got pressures, volumes, moles, and temperatures. So that tells me that I need the ideal gas law. And my pen is not working. So let's try that one more time. All right, let's try this. There we go. P equals V equals nRT. Volume, 4.2 liters. Notice if that was not a liters, we'd need to change it. Moles, 0.023 moles. I'm going to solve for my pressure in atmospheres. So I'll use this value here for R. I usually stick with atmospheres unless I'm told otherwise. And then my temperature is 293 kelvins, right? So I will need to divide all of this by 4.2 liters in order to solve for my pressure. Look at your units. Moles cancel, kelvins cancel, liters cancel. We're left with atmospheres. And yes, that is an appropriate unit. Okay, so what's our answer? It's 0.023 times 0.08206 times 293 equals, divided by 4.2 equals, and I've got 0.132. So pressure, let's change my color. Bad color. No, 0.132. My bad. Totally read that wrong. 0.132 atmospheres. Oh yeah, that's what they have right here. Yeah, we should only have 2 sig figs, so 0.13. All right. All right, let's look at another one. Let's go ahead and just look at this one right here. How many moles of chlorine gas, so chlorine gas is Cl2, right, would occupy a volume, okay, so that's our volume, is 35.5 liters, moles, at a pressure of 100.0 kilopascals and a temperature of 100 degrees Celsius at 273, 373 kelvins. And then we need to also get the grams of chlorine. Okay, well, once again, just, look at your units. You've got pressures, volumes, temperatures, and moles, and nothing's changing, right? We don't have a set of changing conditions. So let's go ahead and utilize the ideal gas law. Let's plug in our numbers, right? Pressure is 100.0 kilopascals. Our volume is 35.5 liters. We need to solve for the number of moles. Our R value, well, since our pressure is in kilopascals, our R value will be 8.31. All right, 8.31 liters, kilopascals, moles, Kelvin. And our temperature here is very high, 373 kelvins. Okay, so we're going to need to divide both sides by the 8.31 and the 373, right? So that those cancel. Look at your units. It's the fun part, right? We'll see that kilopascals is gone. Liters is not gone. Kelvins is gone. And liters is gone. And we're left with moles. Dividing, that'll give us the inverse appropriate unit. Okay, so let's do the math. 100 times 35.5 equals, divided by parentheses 8.31 times 373, close parentheses, equals. That gives me the number of moles of Cl2 equal to 1.14. All right. However, it also asks for the mass of Cl2. So I will say 1.14 moles of Cl2. And I will use my molar mass to convert my moles to grams. Every 1 mole is 70.90 grams. 2 chlorines, not just one. 1.14 times 70.9 equals, that gives us 80.8 grams. Grams of what? Cl2 gas. All right. They probably have a slight variation on their R value here. I'm not going to worry about it. Okay. Ideal gas law, you're going to use it when nothing's changing, right? Your volume's not changing, your temperature's not changing. It's an equation of state. At this given moment, when these variables are given as such, what will this be, all right? And don't forget that we now also have this right here. We know that 1 mole of any gas is equal to 22.4 liters. That is the molar volume of a gas. And that is only true at STP. And that's when the temperatures and the pressures are standard. You know that 1 mole is 22.4 liters. So you could think about it like this. At STP, how many moles of gas in 2.5 liters? Well, at STP, 1 mole is equivalent to 22.4 liters. So how many moles would be equivalent to 2.5 liters, right? So we would see 2.5 divided by 22.4. And we would have 0.11 moles of gas at STP in 2.5 liters, okay?